All right, continuing chapter 16 material. The other issue that comes up in chapter 16, besides common ions and solubility product constant, is sort of a subset of the common ion effect, or common ion problems, which is called a buffer. So a buffer solution contains both a weak acid and its conjugate base, or you can think of it as a weak base and its conjugate acid as well. And there are certain simplifications you can make in doing a calculation when you're in a buffer system, because in a buffer system, there's not going to be a big shift in one direction or another. Now, I think the best way to see how a buffer changes the calculations a little bit is to look at progressing through a series of solutions. So the next few videos, we're going to look at doing a titration between a weak acid and a strong base. We'll start with a solution of just a weak acid. As we start to add the strong base, we'll see that it'll transition into what we would describe as a buffer solution, right? But then eventually we'll have used up all the weak acid, we'll get just a basic solution, and then as we continue titrating, the weak base will eventually be gone, and then we'll have a strong base. So on the notes, I've got this problem kind of split into 6 different parts, right? We're starting with just a sample of our acid, right? And then each part is representing a different amount of the titrating solution, the strong base or sodium hydroxide being added. So the first problem here, part A, is before the titration has actually started. Right? So in our Erlenmeyer flask, we've got just our sample of acid, probably some indicator so we can recognize when the titration has hit the end point or the equivalence point. But we just really want to calculate a pH of where does this titration start when we just have the weak acid around. So our acid is benzoic acid, but we've mentioned before we don't really need the formula of the acid, so I'm just going to use HA as sort of the generic for a weak acid. We should be well familiar with that equilibrium. The weak acid is going to protonate the water to make hydronium ion, and there will also be the conjugate base of the weak acid, A- in this representation. We can start to fill in an ice chart to figure out how we can solve for the concentration of hydronium, which will relate to our pH. So our initial concentration here is 0.25 molar in weak acid. There are no products yet, no common ion or anything to worry about at this point. We don't know anything about equilibrium, so we're going to use X's. Some of the weak acid will react, so that would be minus X. It'll produce hydronium and conjugate base, so each of those would be plus X. Now, if we look back up here, we can compare the concentration of our weak acid to the equilibrium constant to see if we can make the assumption that that X can be ignored in our calculation. So if I take 0.25 and divide by 6.3 times 10 to the minus 5th, I get 3,968. So that's an indication that that is a good assumption. So we get greater than 1,000. So I'm going to ignore the minus X there. And that means at equilibrium, I would have 0.25 for the concentration of my weak acid, and X for the concentration of hydronium and for the concentration of the conjugate base. Plug that into my equilibrium constant expression. So products over reactants, right, like it has been for the last 3 chapters. And we've got all that data. We've got Ka here, 6.3 times 10 to the minus 5th. Hydronium and the conjugate base we both called X, so that would be X squared on top. And for the weak acid, that initial concentration is 0.25. Okay, if we solve for X from that equation, so start with 6.3 times 10 to the minus 5th, multiply through by 0.25, then take the square root of each side of the equation. We'll end up with X equal to 3.97 times 10 to the minus 3rd. I think that would be a molarity. This is the hydronium ion concentration of the solution, so that will get us to the pH. We take the negative log of the hydronium ion concentration, and the pH of this solution is 2.40. Okay, so kind of nothing new there. That's something we would have been able to do as we were going through chapter 15 material. But this is important because we're going to want to compare that value to what happens in the subsequent parts of this particular problem. If our solution starts at 2.4 and then we start to titrate by adding a base, the pH should go up. So we should always have some idea of what's going to happen in the next step, because the pH should go up from 2.4. You might be able to recognize if something went wrong in your calculation if the pH does not come out in a reasonable range for the position within the titration that you're looking at. Part B, pretty long, so we'll put that in the next video.